Basically, that's just an example showing you that, hey, I didn't blindly predict SP2, but there's something else going on there. Okay, we've got some two handouts today. We'll get started. One here. And one here. It's two different handouts. One of them is acid base, which we'll start today. The other will be our next outline. Not really outline, but set here. There will be another outline like the green sheet next time. Okay, any questions while I'm getting this out? See where we left off. Questions? Hopefully you have your questions written down, and hopefully you've generated a lot of questions. To me, that's the more you study, the more questions you should have. If you're not generating questions, you're probably not looking at stuff in detail enough and asking yourself questions. Okay. Physical properties. That's the one we're in. Okay. There's warm-up questions there. Hopefully you look at these, trying to answer these. These are basically problem sets to work on your own, SI. On the Tuesday, Friday question.
Can we go over C2BR4?
I can't hear.
Can we go over C2BR4?
C2BR4. Is it polar or not?
I got
Non-polar? Get a Lewis structure?
yeah.
I'm pretty sure it'd be non-polar. Yeah. Lewis structure was an alkene with bromines on each carbon? Yeah. Non-polar? Good. By the way, I brought a quick look at models. These models are a little bit bigger than what you'll be able to purchase on your own. So this is a tetrahedral. We looked at dipole, like carbon tetrachloride, carbon with 4 chlorines. A tetrahedral arrangement would be nonpolar. Chlorine all around. If we go back to carbon tetrachloride, 1 chlorine coming up, so we have a dipole going this way. And then we have 3 dipoles going down, but to the side. But all 3 of those sum to 1 dipole straight down, and that cancels that stronger dipole straight up. So CCl4 would be nonpolar. The other thing I want to show you about the tetrahedral is make sure you know how to draw one. And every time I draw one, I'll typically say, what? 2 in the plane. See those? Right there. Okay, 10 the boards here. 1 straight up and 1 that way in the plane. Then what do I have? 1 forward. We draw the 1 forward, bolded. And then what do we have? The one back here. You see it going back? And we draw that one sort of like this. Sort of tailing off. So there's your tetrahedral. Turn the plane, 1 forward, 1 back. There's your bond angles. What's that bond angle right there? Supposed to be 109.5, all those bond angles. My model for the SP2 is more like what you'll have or buy. It's smaller. Fortunately, they don't make nice ones here. This is an alkene, carbon-carbon double bond. We'll show it on the board. Hybridization of each carbon. What's hybridization? SP2, 3 hybrids, trigonal planar. So that's all. This is all planar in the board. There it is there. See how it's flat on the board? You can see that guy? Trigonal planar, boom, boom, boom. Sigma bond here, coming from the hybrid, also the pi bond. Both carbons are planar. Because that's planar, that's a flat molecule. It's going to lay flat. Okay? All on the plane of the board. Why? I can turn this. So, see, these p orbitals are coming out. And they're overlapping on this side of the board and that side of the board to make that pi bond there, the second bond. Okay? They're coming out. Now, instead of this on the board like this, I'm going to turn this like this. We turn that like that, and then we can show these straight up. Because the remaining p orbital is perpendicular to the plane of the hybrids. So they're straight up. And again, this is kind of small. But they're overlapping side to side. And that's the pi bond. Now, because of that, these can't rotate. If we try to rotate this, we'll break the pi bond. It's no longer side to side. Okay? So that cannot rotate like this. Where on the other hand, if there was just a single bond between, this is where we put two more H's and make that a single bond, this can rotate. Okay? Because that's a single bond and it's head to head and it can rotate. We'll look at this rotation a little bit later. But this guy can't rotate. You'll break the pi bond. And so it's fixed. We'll mention that a couple more times. Let's look at where we left off at. Hydrogen bonding? A hydrogen bond is nothing more than a strong dipole-dipole interaction between an H. The H has to be bonded to what? O, N, or F. Typically O or N. And then in hydrogen bonds, that H forms a non-covalent interaction with what? Essentially, the H that's on an O, N, or F forms a non-covalent interaction with the lone pair that's on an O, N, or F. And so we can show a non-covalent interaction because obviously the oxygen is partial minus, all because it's electronegative there, but also because it has electrons. Electrons are minus. But those electrons, that minus, see this is a dipole here. So there's a lot of partial plus on the H, and we can show a hydrogen bond non-covalent interaction between the lone pair that's on an O, N, or F with an H that's on an O, N, or F. And in the hydrogen bonding network, that's what I'm showing. All these molecules of these alcohols, strong intermolecular attraction. The H that's on one is hydrogen bonding to the O of another. And so they're holding hands by hydrogen bond. Pretty strong holding hands. Hydrogen bond is everywhere. It explains a lot. Explains why your DNA is double helix. Okay, on the next page. Some questions about hydrogen bonding. This is diethyl ether. Can it hydrogen bond to itself? By the way, with hydrogen bonding, I don't know if it's listed here. It is listed here. One of them is called an acceptor, one's the donor. Let's make sure it's listed. Okay, it is listed here. The H is the donor part. The lone pair is the acceptor. What do you have to have the hydrogen bond? A donor and an acceptor. Okay? Just like Velcro, what do you have to do for Velcro to stick together? You have to have a fuzzy piece and a more of a non-fuzzy piece, right? What if you have two fuzzy pieces? Do they stick together? No, they don't. Okay, it's a similar idea. Basically, can this hydrogen bond to itself? No. I see a hydrogen bond acceptor. oxygen lone pair. Do you see a hydrogen bond donor? Do you see an H that's on an O, N, or F? No, I only see H's on carbons. Those aren't polarized enough to do hydrogen bonding. No, it can't hydrogen bond to itself. Now, it can maybe have some dipole interaction because there is partial negative here. There's a little partial positive there and a partial minus because of the dipole. And the partial plus of one molecule can associate with the partial minus of another. That's not a hydrogen bond. That's not as strong as the hydrogen bond. So we don't describe it as a hydrogen bond. Okay, can it hydrogen bond to water? What if you put this in water? Can it hydrogen bond to water? Yeah. By what way? Would this be the donor or the acceptor? Obviously it's only the acceptor. So it would hydrogen bond to water how? Water would be the donor, okay? So if someone says, hey, can ether hydrogen bond? You need to say, well, could you clarify your question? Are you talking about to itself or are you talking about to another solvent? All right? General questions. How many H bond acceptors and donors are present in the antidepressant effexor? How many acceptors? And this could be a little like, somebody may want to clarify the question. How many acceptors? Okay, does anybody want to clarify that anyway? I see 3 heteroatoms. Question, Zachary?
I was gonna try to clarify.
What's your question?
With the OH, the hydroxyl group be donor since the H is already there.
Well, it can also be an acceptor because the oxygen has more pairs. Okay, so one clarification. What's another question you might have about this?
Oxygen conjugated?
Oxygen what?
Is it oxygen conjugated on? Because, or is that only for nitrogen?
That is conjugated. How does conjugation affect this?
Does it get free?
If the lone pair is conjugated, is it a good hydrogen bond acceptor? Not as good. But that makes this a little fuzzy. The question I was hoping to see is, hey, there's 2 lone pairs here. You count that as 1 acceptor or 2?
One.
It probably varies.
Depends on concentration.
It probably varies. Some people may call it 1, some people may call it 2. Okay.
What about nitrogen?
Well, there's only 1 lone pair there, so it's just 1 acceptor. So for the oxygen, you count that as 1 acceptor or 2. This is a question where you're not going to see this on the test and get it wrong because you didn't know what the answer was there. But this is part where you have to be, okay, what's going on here? Okay, you question things. What we don't want to do is just learn, okay, boom, 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 and never even look at all these things. And so when you get out in the real world and start talking about it, you're like, all right, but it is 2 lone pairs. Okay? Let's look at some effective hydrogen bonding. This is just some examples. Why is the boiling point of this alcohol so much higher than that ether? Starts with an H. Hydrogen bonding. See, these molecules are going to be holding hands very strongly by hydrogen bonding. Can that hydrogen bond to itself? No, there's no acceptor and donor. So those molecules aren't going to be holding hands quite as tight. Why is this boiling point higher than that one? They're both amines. This amine can hydrogen bond to itself because it has an acceptor, the lone pair of nitrogen. It also has a donor, which is an H on a nitrogen.
So is it the same thing where you would say, is that 2 donors, or do you consider that to be a big fuzzy question?
2 donors?
Yeah, that would be it.
Probably 2 donors. You could show some hydrogen bonding for both H's.
When you say,
Maybe in an enzyme, one H is hydrogen bonding to carbonyl of an amino acid, and the other H is hydrogen bonding to water. So yeah, probably so. Question?
Yes, sir. When you say can hydrogen bond itself, you mean there's another same molecule, right?
Yeah, because if we're gonna boil this, you got enough to see, right?
Mm.
If you got enough to see, that means you got like 100 bazillion molecules. Okay? And so, yeah, there's plenty of them all there. Obviously, if you only had one molecule, it couldn't hydrogen bond to itself. Okay? If you got one molecule, you ain't got enough to distill or boil. Okay, why is water so much higher than H2S? Very similar. Actually, this is higher molecular weight and has probably more surface area. But water does hydrogen bonding very strongly because it has two donors. Okay?
So is that due to electronegativity? Because oil is more electronegative?
Sure, that's why we said the H has to be on the O or N, because the O or N is more electronegative, making the dipole quite strong. See, the S is not electronegative, and so the dipole here is not as strong, and so it doesn't get called a hydrogen bond. It would only be a dipole-dipole interaction. But as we said, these are listed in order of strength. Right there, hydrogen bonding is the third strongest. And in fact, if you see hydrogen bonding, it should be your answer, and you don't say, oh, that one's bigger. It's like when you're playing cards. Aces beat jacks, okay? You got hydrogen bonding. Probably even if you had a huge molecule with lots of surface area, probably the hydrogen bonding is still going to be better. Because that surface area stuff is very weak. And of course, I could show you a compound that was so huge, it had so much surface area, that it might be higher boiling than something like this. But in general, go with your strongest phenomenon here, or your strongest intermolecular attraction. That's usually going to give you your answer. That's the first thing you want to consider. Mike?
Why does methanol have a higher boiling, or a lower boiling point than like ethanol? If the hydrogen bond is making up a greater portion of all the bonds?
Both of them can hydrogen bond, so you got to look for something else to give you your answer. Okay? Both can hydrogen bond to itself, so that doesn't answer the question. So what else do you want to propose? But this one's bigger. So there you have a second thing that gives you your answer.
Dispersion.
Yeah, it's bigger. So this has more van der Waals. Hydrogen bond is a wash. They both can do that. So you got to look for something else to give you your answer. Right? But I would start with hydrogen bonding. Okay, down here, that's an OH, got cut off there. Very similar molecular weight and surface area, but why is this diol 200 degrees higher boiling point? Hydrogen bonding, okay, that's antifreeze, okay? Here, no hydrogen bonding, no dipole, all it has is that weak van der Waals, not much attraction. All you gotta do is put a little bit of heat into it, and it'll be boiling. Okay, I mentioned DNA. What holds your DNA together to double heated? Hydrogen bonding. Hydrogen bonding, take a look at it. Your fourth intermolecular attraction, intermolecular force, or IMF. Ions. This is where you have actual formal ions. It's going to be your strongest attraction. Sodium chloride, the boiling point is 1400 degrees. Have you ever seen salt boil? Okay? Very high. It's ionic. Not only are the sodium and chlorine tightly attracted to each other, but you also have other ions. They all are attracted to each other. All the ions, and you actually form like a lattice and a crystal structure and stuff. Very tight. You actually have not partial minuses, but full minuses.
Is that why salt water tastes?
Question?
Is that why salt water is harder to boil?
Now, salt water is, you're not really boiling the salt. The salt increases the ionic strength, the osmolarity or something like that. It's a phenomenon related to dissolved concentrations. For example, here, ethanol boiling point is 78, it's a liquid. If you make this ionic, like a sodium salt, the boiling point is greater than 500 now. Okay? And it's probably going to be a solid. Things that have super strong intermolecular attraction are more solids. In fact, we can now go to the melting point. We were looking at boiling, going from liquid to gas. Well, the same thing with melting, going from solid to liquid. To go from solid to liquid, you have to loosen the intermolecular attraction and to make it kind of fluid, a little loose. But it's the same idea. The more intermolecular attraction, the higher the melting point, in general. So let me ask you, which one of these would you expect to have a higher melting point? They're both amides. One of them is 44, one of them is 126. It's like we're playing The Price is Right. Which one's 44?
Right.
Who says right? Okay, good. 44. Why?
No hydrogen.
Because this guy can hydrogen bond to itself. It has an acceptor. Actually has more than one acceptor. And it also has donors. An H that's on an O or N. Does this have acceptors? Yeah, it does. But what does it not have? It don't have an H on an O or N. What does that mean? It's a methyl. What's a methyl? It's a CH3. Okay? I usually do ME. We'll do nomenclature probably tomorrow, next day. It can't hydrogen bond to itself, and so it's not holding hands as strong. It's easier to break the intermolecular attraction enough to get it to be fluid with each other. Make sense? Next topic we'll look at is solubility. Dissolving compounds. Very important, as I mentioned. If you want to dissolve a drug in an IV bag, get it dissolved so you can give it to a patient. If a drug molecule won't dissolve, it's probably not going to be a good drug. Just go into the the stomach, never dissolve, just get eliminated right out. Never get absorbed. One main thing to start with is like dissolves like. More polar the compound, you need a more polar solvent. Okay, we're dealing with solvents here to dissolve the solute. So like dissolves like. Question to get us started. The amides above, the two amides, which one would be most soluble in water?
Left.
And we say like dissolves like, we're like meaning it has similar intermolecular capabilities or potential intermolecular attractions that it can associate with. Tell me again, which one most likely soluble in water? One on the left. Why?
It's got hydrogen bond different.
Hydrogen bond. Because the one on the left can hydrogen bond to water. Can the one on the right hydrogen bond to water? Yes, it can. Right? I mean, I could show that lone pair associating with the H of, there you go, it's an acceptor associating with a donor. You can hydrogen bond too. But what's the difference in the two?
That one has a left one has a donor and acceptor.
This has more hydrogen bonding capability. Because we can show this one doing the same thing, okay? We draw these H's out. We can also show something like this. The one on the left has more hydrogen bonding capabilities. It has both acceptors and donors. Does that make sense? And so it can associate more with water. It'll like water more. It'll interact with water more. It'll dissolve more. Now what we're not doing here is absolute. Is this soluble in water? You know, it may not be. Because it does have a lot of just plain hydrocarbon, which doesn't like water, because that's nonpolar. But it wasn't an absolute question. The question was relative. Which one should be more soluble? That one. Is it? I don't know. You got to go to the lab and try, but it would be more than that one. Which one would be more soluble in hexane, which is just a plain saturated hydrocarbon? 1, 2, 3, 4, 5, 6. Does this have any polarity? Thus, is it going to like polar solutes? It's like, it's going to shun it. I'm not interested in polarity. There's no reason I want to play with a polar compound. So which one would be more soluble in hexane? Well, on the right. You might say because it has less hydrogen bond. What does the one on the right have more of? It has more of these hydrocarbons, these CHs, which are just kind of blandness. And the more of that blandness you have, the more it's getting nonpolar. And the more it's starting to look like this, and it's like that, like. Is that one soluble in hexane? I don't know, but it's more soluble than the other one. Okay, with solvents, we got to start getting familiar with them. You don't have to memorize these. We'll use them. You should refer back to this here along the way. Some of these we'll learn quicker than others. This is my table. I've divided them into, first, ones on the left I call polar, ones on the right nonpolar. Now, is diethyl ether polar or nonpolar? It's actually a polar molecule because it's got two dipoles and they don't cancel because it's tetrahedral. So why am I calling it a nonpolar solvent? That's because in the real world there's some vagueness in it, okay? All right. I'm dividing these because these are soluble in water. These mix with water. These do not. See, even though diethyl ether is polar, it's not. It's not polar enough to mix with water. Go to the lab, mix ether with water. You'll get two layers. They won't mix. This is an example of the absoluteness. Hey, it's polar. It should be soluble in water. Well, sorry, you're wrong. Because it's apparently it has enough of this plain, bland hydrocarbon that keeps it from dissolving in water. Even though you can say it hydrogen bonds to water. So that's how I divided them. Actually, that's polar. Both of these are polar. That's the argument. Dichloromethane is polar, but it's not soluble in water. The only one over here that's truly nonpolar is hexane.
So how is hexane more truly nonpolar than the toluene?
For you, it's probably about the same, but the pi system can be a little bit polarizable, but don't worry about that. Toluene looks nonpolar also.
Is there a specific reason why we only use hexane but not, for example, octane or hexane?
Hexane has a good boiling point to work with. Pentane, it's so low it's almost boiling at room temperature. Heptane is just a little bit more expensive. It's also hexane, just cheaper. But actually in industry they use more heptane. Because the higher boiling point, it's a little more safer and doesn't catch fire as quick. But just hexane is just a common fraction. Okay, over these, what do we have? Ethanol, acetone. You'll wash your glassware with acetone in the lab. It's actually water soluble. Look how similar it is to that. Actually, if you take off one of these carbons on the end, just make it one carbon, it's now water soluble. But with 2 carbons, it's not. Acetone, acetic acid, that's your vinegar. DMF is a common polar solvent. DMSO is used for NMR. So again, not really to learn and memorize now, but refer back to. And if I refer to solvents in here, refer back to that right there and see those. Ethyl acetate commonly used in lab. But of course, what's the universal solvent? Okay, well, people say it's a universal solvent, but for organic chemistry, it's actually pretty lousy. Well, it doesn't dissolve a whole lot of organic compounds. It dissolves a good many. It dissolves sugar. Of course, you have to heat the water a bit. It'll dissolve an organic compound if the organic compound has a good amount of polarity to it. You know, sugar has lots of OH groups on it. What's water make the best for? Salts, ionics. And if we could turn an organic into an ionic, then it's going to be usually soluble in water, or a good chance it's soluble in water. And you're doing a solubility lab, and so you look for ionics, and if you can get an organic molecule turned into an ionic. And how do you typically get something turned into an ionic? That's going to take us to acid-base chemistry. Okay? And down below is an extraction process. I'm actually going to wait and talk about it a little bit later. It may be also in the other handout, but we'll come back to this. Acid-base chemistry, very important. A couple miscellaneous things before we leave this packet here. Why did we go over these 4 different IMFs? And you know the 4, right? There's 3 others other than hydrogen bonding. Well, they're very important for discussing and understanding how molecules interact. Molecules may be a drug molecule interacting with an enzyme in the body. And that's how maybe cancer is stopped for a certain type of cancer. Or maybe this is how this cholesterol drug, Crestor, you've seen it on TV, right? Every night. Crestor binds to HMG-CoA reductase enzyme. How does it bind? It doesn't bind covalently. It doesn't make a new covalent bond and it's stuck there. It bonds by non-covalent interactions. And here it is. Here's the drug in the receptor pocket. What do we have here? Right here. This oxygen. See, somebody flubbed this up. What is this? Looks like a hydrogen bond between oxygen and oxygen. But we know better, right? That's really a hydrogen bond between the O and the what? Yeah, I don't know who did that. That don't make sense, right? What do we have here? You see, they're being just kind of generic. That's not. It's really the long. Now you can do either way here, but the H hydrogen bonding here, and then this lone pair is apparently hydrogen bonding to that H. It's on that nitrogen. Look right here. They've got this anion doing a non-covalent interaction with that positive. You could show that as a hydrogen bond, but it's also 2 ions, and so you can just show it as an ionic attraction, which is actually stronger. So you look at all these. What is this over here? These are amino acids that are in the enzyme. And all these amino acids have side chains that look kind of like that, just hydrocarbon. Why would hydrocarbon want to associate with hydrocarbon? What's the IMF there? Yeah, that's just some van der Waals, hydrophobic. They call it hydrophobic bonds. Okay? I'd rather they call it a hydrophobic interaction. A covalent bond. But your hydrocarbons will interact by van der Waals. Okay, take a look at that, see if any questions come up. There's other miscellaneous things down here. Soap, micelles. Soaps typically have a polar portion and a non-polar portion. Why is that? Because when you're washing, typically a soap removes oils. Oils are hydrocarbon. So this part likes the oil. What does that part like? Water from your shower head or whatever. Now, if you were bathing in acetone, you wouldn't need that. You could just wash the oils off with acetone. But we don't bathe in acetone. So it's sort of like, it has two parts. Part that likes water, part that likes oil, everything gets... Okay? Take a look at some of these applications. Two more. Here's two drugs. One's called Prilosec, one's called Nexium. What's the difference in these two drugs? Other than a lot of money? The only difference is, here you have an NH, here the H has been removed and you have a nitrogen anion. Since you have an anion, you gotta have a plus. Plus is magnesium, since that's 2 plus, you gotta have 2 of these. That's why that's in brackets. The only difference is, this is a salt, and this is a neutral molecule. Which is more soluble in water.
Two.
Everything's the same except this and this.
The salt.
More ionic. Ionic's good for water. Now you say, well, can't this hydrogen bond to water? Yeah. But so can this. There's 2 lone pairs there. So, but remember, ionic is your strongest, and water is great for ionics. If we can make a drug ionic, more soluble in water, majority of your drugs are ionic, because your body's water-based. Now, don't tell anybody, but when you take this and it goes to the stomach, what's in the stomach? Acid. And this is just going to protonate, and then it forms this in the stomach. But of course, you pay more money for that. The drug company got a new patent on this. I think they claimed that this dissolves faster in the stomach. It's ionic. But as soon as it dissolves, it converts to this. There's no difference in the body once it gets absorbed. Last thing. I may show this a little bit later after you have time to think about it. Okay. Also, I want to show you the colored version instead of black and white. Take a look at that. There's a question there you can answer. Question on the back. Inductive effects. What is an inductive effect? Inductive effect is basically a dipole effect. When we drew a dipole and we said the oxygen is pulling, or it's electronegative, we could also say it's inductively pulling. Okay? Dipole consequences are just called induction. So an oxygen is inductively withdrawn if it's bonded to an H. Or carbon or nitrogen. Okay. Let's move on to acid base. Everybody get handouts today? If I got 2 handouts? All right, let's see how we do before we even do acid base. Maybe we don't need to cover acid base. Can everybody answer all these? If you can, maybe we can just skip the lecture. Which anion is more stable?
Second one.
Which alkoxide is more stable? Obviously, the difference is chlorine versus chlorine. Which bond? O minus is more stable. You got a good chance of getting this right. Remember, guys, all this stuff builds. Okay. Which one's more stable? Somebody over here said that. The fluorine compound? Why? Stronger inductive withdrawing? Yeah. What kind of dipole do you have here? What does this fluorine do? It's a greedy, okay, something, SOB, greedy SOB. It's the most greediest up there. This fluorine's doing what? Is it donating or withdrawing? Yeah. Not only does it withdraw here, but the effect sort of comes all the way through here. Okay? No, not just on the one part, but it's felt all the way through. It's like tug of war. You got a big guy on the end. There's people way over there going to feel it too. Right? Chlorine withdraws, but not as much. How do we stabilize a minus? Things want to be neutral, so we got to make it more towards neutral. How do you make it more towards neutral? Pull the electrons away. Now you can get rid of the minus, but then that'd be a different compound. Then you say, well, how are the electrons pulled away? Well, this goes back to, well, really, what is a dipole? See, all these single bonds in here are not evenly distributed. They're more towards, you see, they're kind of more towards that fluorine. I can't really illustrate it, but all these bonds are distorted towards the fluorine, more as you tail off. And so that makes some of these electrons come this way, and it gets a little fuzzy because you're like, well, I thought all the electrons were right around the oxygen. No, they're sort of spread through the bonds to a degree, and that's enough to give us an argument to say that's going to be more stable because the electrons are more pulled away. Okay? You got a great shot of answering everything on this page from just what we talked about this far. All right? Simple thing. You got to remember the things we talk about this week help us answer things next week. All right. We got to be able to do questions like this. This drug here, Ultram, if it's treated with HCl, what will be the product? Well, HCl is a acid. Okay, good. So, if the drug is going to react to the acid, the drug is going to act as a base. You see how we're making progress already? So if it's a base, let's check one. What component of the drug is the base? And everything we're doing here, when I say acid-base, we're doing Bronsted-Lowry. Okay, we're doing proton acid. H+. HCl is a source of H+. Where's the base? Now you might generically say this reaction, you get, okay, in organic chemistry we get very structure specific. Okay, the H+ is going to become bonded to what atom? Somebody said OH, I've heard it twice. Why OH? Hydrogen acceptor? Why? Okay, it does have a lone pair. So does the nitrogen, so does that oxygen. I mean, which one? Why did you say lone pair? Because the lone pair is the thing that accepts the H, that bonds to the H, so that's good. Look for an atom with a lone pair. But which atom is most basic?
The nitrogen.
You'll know how to determine which is more basic? What did you learn, Jim Kim, about basis?
They accept, it should be the one that wants it.
What's a good base? What's your favorite base from Gen Chem? OH. Okay, well, OH is minus. I can really see why that might like a plus. I don't have a minus here. So why is this a base? Because it can do what? This can give up a hydrogen? Well, that would be called an acid. Acids give up hydrogens. Yeah, I mean, accept, but why does it accept it?
So you'd rather do that than a
It's
carbon.
more electronegative than nitrogen.
I think we need to talk about this a little bit. Okay, acid-base mechanism. Hopefully you know this from Gen Chem. We got some base, and it's an atom that's the base, and not the whole molecule. It's an atom. It's going to have a lone pair. The lone pair reacts with the H. Okay? Now the H is going to be bonded to something, because H plus don't exist. It can be bonded to water and be H3O plus. Sometimes you'll see it written like this generically, typically it's bonded to something. But the mechanism involves the lone pair making a bond to H. What does this arrow mean? WDAM.
Donating electrons.
It's right here. It means this. The lone pair of the basic atom makes a covalent bond to the acidic hydrogen. Okay? These electrons, every time I use an arrow, and especially with a lone pair, these electrons make a bond to H. And so now, the base has made a bond to H. There it is. Well, H can only make one bond. So these electrons are going to get pushed off of the H onto the Z and becomes what on the Z? And Z is just the atom that's bonded to the H. You're going to have a lone pair on the Z. Now typically, for this to be acidic, you're going to have a dipole here, and Z is going to be electronegative, making this a lot of plus. And the Z, because it's electronegative, is going to like having an extra lone pair. This is your standard acid-base mechanism right there. That every acid-base reaction we do, you should do that. If you don't learn in this acid-base mechanism, you're going to have difficulty. Y'all did this in Gen Chem?
Not this big enough.
You know, not this.
How to do an acid-base reaction? This is your acid-base reaction. Okay? You got to keep track of charges, though. I showed no charges in the acid-base reaction. Everybody know how to determine a charge? We did that. You practiced it already, yeah? Okay? Unfortunately, when we start doing it, you will all have charges missing or wrong. And I wonder why. Is anybody not clear on how to do a charge? Okay? I think you just forget about it or something. Never forget about your charges. Okay? All right. Let's look at this, some background. I'm sure you saw this. You did calculations out the wazoo in Gen Chem, right? HA is an acid. It can ionize to give H plus and A minus. Ionization. That's very generic, and actually H plus don't really exist. But you looked at Kas, okay? And you know that stronger the acid will have a higher Ka. Conversely, where does it say pKa? A little bit lower. Because we use pKas, here's your take home. Stronger the acid will have a what? Lower pKa. We have to use pKas because we will quote them to illustrate or to know strengths of our acids we're dealing with, especially relatively. Here's some approximate pKas. HCl is a strong acid. pKa is like -7 or so. Strong acid. This is a carboxylic acid, actually acetic acid. You know that functional group. pKa about 4. Okay, it's a weak acid. It's your most common organic acid. This is an alcohol. And alcohols are considered neutral. But guess what? Anything with an H can be an acid. It's just how strong of a base is required for it to be an acid. Those are considered acids. These can act as acids. pKa of an alcohol is about 16. Okay? We get to this, hydrocarbon, pKa is greater than 40. It's nearly never acidic. There may be something you could show for that to be acidic, but okay? There's a list of pKa's in the back of your workbook lab manual. Those four should be there. How do we judge acidity? Why is that compound more acidic than this one? There are 4 reasons. 4 things we look for. Listed here. Okay? We will cover these one at a time.
So
Tom?
is this why HF is a weak acid even though it has a stronger inductive effect? Because of the size of the atom?
Yes, we will see that. We will see that. Okay, number 1, electronegativity and size of the A. Now here I use A. On the previous sheet I use Z. They're both commonly used. Neither one are on the periodic table. Okay, first thing is electronegativity. Water versus HF. Which one's a stronger acid? HF. Okay, why?
It's more likely to donate to
Yeah. That's really the definition of an acid there. Why is it more likely to donate pH+?
That's weaker.
Okay, well guess what? It's electronegativity. All right, see it underlined right there? Now, what you want to consider with your acids is this. Where is it going? Now, every acid gives up an H+. But we need to look at the other thing, because the other thing is what's going to differ. If water gives up an H+, what does it form? Hydroxide. If HF gives up an H+, what does it form? Okay? When those act as acids, they form these. You want to look over here, the conjugate base, and say which is more stable. Now both are minuses. Which is more stable minus? The one on the more electronegative fluorine, which really likes minus, or electrons, or the one on the less electronegative? More stable, because it's more electronegative. Thus, this guy is more eager to give up the H+ and form that. I want to become minus. Take my H. Oxygen doesn't want to do that quite as much. It's electronegativity argument. Okay? Water versus ammonia, which is a stronger acid? Well, where are we going? What does water form when it acts as an acid? Is it written there somewhere? We really want to consider this versus what? What does that become when it acts as an acid? Does everybody understand how we get to this point? Because if we take away an H and a plus, okay, if you take a plus away from that, you've got to be left with a minus. Take away the H. Now, there's going to be 2 lone pairs. How do we get to that point? I feel like I should show that because there's got to be some base. How do we get that? Here's our base. What does it do? If ammonia acts as an acid, we go back to the previous page. The lone pair takes the H. There's a lone pair there. What happens here?
Leads to another one there.
On the previous page, these move on to nitrogen. What do you get? You now have a nitrogen with 2 H's, 1 lone pair,
Another one there.
another lone pair. There you go. That's what you get. All right. Same thing with hydroxide. That's how you get hydroxide. 2 lone pairs, you end up with another lone pair. Which one's more stable? O minus or N minus? Well, which one likes minus better? Oxygen, more electronegative, more stable. Which one's more willing or eager to give up the H? In this case, that one. Nitrogen's like, hold on, I don't want to become minus. I don't like it as much.
So the thing you drew right there, the base gave a lone pair to NH3.
No, the base took the H.
Okay,
The bonding pair
became,
moved on. These two electrons got to go somewhere. Because this makes bond to H. But those two electrons were originally a lone pair. Well, where do these two electrons go? They move on to the nitrogen and the second lone pair. Okay? That's why I say you've got to learn. It's right here. That's exactly what we did, but this is generic. See? These electrons move on to Z as another lone pair. Z could have started with one or two lone pairs and they would have had two or three over there.
so with your, what does arrow mean? Does that mean that you always want to explain the arrow, or do your arrows always mean the same thing, like in similar situations?
No, we will use arrows to show electron movement. Alternatively, I will see some of you guys do something like this. What is that supposed to mean?
The H goes on.
No. What does arrows show?
Like,
Arrows show where the electrons go, not the atoms. Okay? So I'm like, I don't know what that means, because are you saying these electrons move on to the B and this becomes B with a lone pair, and I don't know what it means. Try to explain what that means. The electron flow was shown on the previous page. And as we move forward and start doing reactions, we will do mechanistic arrows, and you need to learn how to do it. First, because it's a requirement of the class. Second, it's like in math learning a formula. It helps you keep track of everything. I mean, in math, don't you want to usually have formulas that you can sort of use? This is your formulaic approach to moving electrons. The other thing with well, number one, the size of the atom. Which is a stronger acid, HCl or HBr? Why HCl? Because you're forming what? You're forming Cl minus and Br minus. Which one's more electronegative? Cl, higher on the periodic table. So you might think chlorine's more stable because it likes minus more. Well, here you'd actually be wrong. Because here, size of the atom is actually more important. Turns out Br minus is actually more stable. Why? Because the minus charge is spread over a larger volume. When is size more important? When you're going up and down in the periodic table. Okay? You're in the same group. How do we know that size is more important than electronegativity? Because if you go to the lab and determine pKa of HBr, you'll see it's more acidic. So we have to explain it somehow. Which is more acidic, HBr or HI? The I minus is going to be more stable than Br minus because the I minus is larger. HI is your strongest of your HX acids. What's the most acidic H in this compound? I have H's on oxygen, sulfur, nitrogen, and plenty on carbon. Which is the most acidic hydrogen? Because guess what? A strong base is going to take the most acidic one. OH? Let's do these two. Which is a stronger acid, OH or NH? OH. Would you rather make an O minus or N minus? O minus, more electronegative. Okay, we're going side. Would you rather make an O minus or an S minus? S minus, because it's larger. That's your most acidic. We ruled it out. We ruled the others out. Now your CHs typically aren't that acidic. You think you're going to want to make a C minus? No. It's a very special case. Well, there's lots of special cases. But in general, your heteroatoms Maybe most specific. H is on heteroatoms, because your heteroatoms are your more electronegative. Okay, the second is inductive effects. I already said what inductive effect is. It's basically electronegativity. Okay? Here's two alcohols. Which is more acidic? The only difference is this has an F here. Well, we really want to consider the conjugate bases, right? That's what I told you to do. Which minus is more, would you rather have minus on oxygen or oxygen? It's the same. You got to look for something else. Well, what do you got going on here? I see this fluorine out here. What does it do?
Pull the electron.
Pulls, and so we can show a dipole, not only there, but all the way through. It really doesn't have anything pulling. I'm actually showing donation there. This is very important, and it's not intuitive, it's just something we have to state. Here we go. An sp3 carbon is actually a donator. An sp3 carbon inductively donates. Not much. Typically we make that argument. So that's why I showed that this out here actually donates. Or you don't even have to consider that. The difference is the fluorine pooling. The fluorine pooling, which O minus is more stable? This is just like the one we did on the warm-up page, right? Isn't this more stable? No. So what does that mean about over here? Which one's more willing to become minus? This one's more willing to become minus. It's more willing to act as an acid and give up the H+. Okay? That's an inductive effect of the fluorine, making it more acidic.
If you were to put a then double bond on that C, on the one on the right, would that mean that there would be less inductive effect?
Yeah, an sp2 carbon is not as strong a withdrawal.
So if you compare the two, you would accept that one?
I mean, a donator. An sp2 carbon is actually almost a withdrawer. Which is more acidic, methanol or ethanol? What's the difference? This has an extra what? An extra sp3 carbon. What do we know inductively for sp3 carbon? Actually donates. So which is going to be more acidic?
Left.
What do we really need to consider? Minus. Which minus is more stable? That minus or this minus?
That.
This one. Because this minus, is this donation making it more stable? No, it's hurting it. You don't stabilize a minus by pushing electrons towards it. That hurts it. That one is not going to be as likely to give up this one. Okay? So this is inductive effects. Withdrawing or donating. Understanding that if you got a minus, how do you stabilize a minus? You got to withdraw. You boil it down to pretty simple things. Which is more acidic, ethanol or this guy over here, which is kind of called T-butanol? Well, that inductive by the sp3 carbons, if you have branching, it's almost like you can do this. All these sp3 carbons are sort of donating all into there. This, even though it's one chain, it's only one donation. It's almost like you got three chains of alkyl groups donating. Lots more donation, so which one's more acidic? Okay. We can have some variation. This is just like on the warm-up page. Which is more acidic? F, because it's going to pull more. I mean, they both pull, but this sort of pulls more. So this O minus is going to be more stable than that O minus. What about this guy?
Less.
This one illustrates that although they're both fluorines, the further the fluorine is from where the minus is going to form, the less the effect. Okay? Fluorine's further away. So as you get further away, the inductive withdrawing sort of tails off a little bit. We'll take a 3-minute break. 3-minute break.
Like, all right,
This
this
has an extra SPP card. What are SPP cards? They're gonna be for donation. Okay, so if this has more donation, is that gonna make it O minus? Where you wanna be looking at the O minus?
right.
Which O minus is more stable? The one that has an extra donation to it, or the one that has not?
See, that's what I was saying, I thought this one would be, because the more you donate, I thought, I guess, the more electrons that were donated, the stronger the stronger.
Different charge, not good. They want to get neutral.
Okay, so, okay.
If you got a minus, how do you stabilize your minus?
Yeah,
You pull electrons away from it.
right, right.
It's not pulling away from it.
Give me, okay,
It's
okay.
donating.
Okay. All right, I got you.
You don't stabilize the minus by pushing electrons toward it.
You got to pull it away.
Yeah.
All right, I got you.
This is more donation. You read it? Does donation help or hurt a minus? Things will be neutral. You don't stabilize the minus. You want to go to neutral.
I don't know the scheme, I only
Donation
know
hurts
that
a
we
lot.
went, no, don't do it last year. You know, we're gonna talk about. He let me in the gate all the time, really. It seems like every time when you get I think it's in the, I want to go ahead
He's a secure one.
I would probably
And
say
like in
more
the,
stable.
like, how you go to.
This is your ass. I don't know how you take it.
Use the secure.
Right.
Oh, there's the.
Yeah, there's a pump.
Okay, guys. Third effect is the resonance effect. Resonance effects. Let's look at this alcohol versus this carboxylic acid. Obviously, that's a carboxylic acid. It's called an acid because it's acidic. That implies it's more acidic than the other one. But why? Well, we want to consider the conjugate bases. This becomes O minus when it gives up the H plus. That becomes O minus when it gives up the H plus. Which one's more stable? Well, that one, because we know that's an acid that should be more acidic. Why is this more stable? It's a resonance effect. Now, you could maybe just get the right answer by saying that while they both have donation from the sp3 carbon line, this has withdrawing by the oxygen, and you may say that that stabilizes this. And indeed it does. But that's just an inductive effect argument. Your main argument is resonance effects. Okay? That's what I explained here. And this is really first look at resonance. I may have mentioned it. So this one has resonance, and this one has no resonance. Now what is resonance? Resonance is p orbital conjugation. Now when we made this a minus, we gave it an extra lone pair. And the extra lone pair led to the increase in electron density, and we actually call it a formal minus. Now, if we can give this lone pair something to do, the extra lone pair, if we can give it something to do, we will really stabilize it. Well, this guy has something extra to do. Before we move on, tell me the hybridization of this oxygen.
SP2.
Okay, I heard 2sp2. sp2. That's correct. Why is it sp2? How many regions around it? 4. So why not sp3? Very good. Because we know anytime a lone pair is next to a p orbital, is there a p orbital here? Yeah, there's 2. The p orbitals are overlapping to make pi bond. Maybe we can draw those in. That's that pi bond that's shown there. Does it make sense, or does it fit what we said, and you'll just answer? One of these, let's put in a p orbital, so we can interact it. And if one of those lone pairs is in a p orbital doing something, we've really stabilized it. It's kind of now bonding. I mean, it's orbital overlap. And that's the answer. What's the hybridization of the oxygen on the top left? What's the hybridization of that oxygen? That's sp3. Why not put one of these in a p orbital? There's no p orbital next door. And you're not going to just put a lone pair in a p orbital with it nothing to do, because a p orbital is higher energy than a hybrid. Unless it's got something to do and interact, it'd rather be in a hybrid. And if it's in a hybrid, it certainly ain't interacting. There's no potential bonding there that it can do, no p orbital bonding or no resonance that it can do. Basically, that's it.
Is this the same definition of resonance that we've been using all along, or the same idea, concept, or is it two different?
A resonance is just one concept. There's just many layers to it.
Okay.
Ultimately, it's p orbital overlap. And a lone pair can be involved in that, and we were showing how. But what we do with, and ultimately that's all it is. Now, as people and not molecules, how do we show this? We show that by showing resonance structures. The resonance structures are actually fake. Okay? But this illustrates how we show the resonance structures. And you need to be able to show resonance structures, because that's just what organic chemists do. Now, there's a dipole here. We said pi bonds are particularly polarizable. We can actually move that pi bond up. What does that arrow mean? These electrons, I'm just sort of taking them and flipping them up onto the oxygen as a third lone pair. What does that arrow mean? It means this. That arrow gives this. Okay? But charge, that becomes a minus. You gotta always be aware of potential charges. It's a plus. What is this? That's just an alternative Lewis structure, where all we did was move electrons, strictly pi electrons. And when all you do is move pi electrons, it's called a resonance structure. We didn't move any atoms. But at this point, these electrons, you remember when we did Lewis structures and we said, okay, this needs a bond? But we don't have any more lone pairs. How do we get that to some bond? These electrons can move in and make a pi bond. But through moving this here, we can show all of these resonance structures. And then we can say, well, which one is best? Which one do you like best? Or which one do you like least? Well, this one has 3 charges. Lots of charges is not good. Which one do you like best? Left or right?
Right.
They're the same.
They're the same. They're the same. What's the true structure of this anion?
Somewhere you should.
The true structure is a blend of all of this. I mean, basically this is a question. Is this minus just sitting right on that oxygen? No, it's really spread out all the way through here, and it's spread onto the other oxygen. We show that right here. Let me introduce a new term. Kendall?
So if the double bond is kind of spread throughout both, would there be like a p orbital on both of them?
What would you say first? If the double bond is what?
If the double bond is spread between both of them, would there be like a p orbital on both of them?
On both of what?
The oxygens.
Yeah. Let's take a little time here. We're getting beyond the answer here, but we're introducing resonance. We'll do this a couple of times throughout the first half of the course, and at some point we'll cover resonance. Okay? But I don't want to just wait and cover resonance because we see it all along the way. We'll build on it. First off, here's the true structure. I'm not going to show orbitals over here. Everybody agree that those are bonded together like this? Okay? That's sp2, that's sp2. We've already said that's sp2. That means everyone has a p orbital. Okay? We sort of knew that already because we see that pi bond. Okay? We say this is going to have a p orbital, and it's sp2. And so what's the geometry? Trigonal planar. Okay, you see the 3 hybrids, trigonal planar, p orbital there. Now, there's one electron there, and that's overlapping, make pi bond. There's 2 here. That's the anion. But guess what? It's overlapping. Now, the one thing we haven't said is once they start overlapping, this really becomes a 3 pi system with 4 electrons. These 4 electrons are equally spread over there, just like if you put 4 quarts of water in a hose pipe and laid it flat. The water would spread out through there. It is influenced by electronegativity. Are the electrons going to be more towards this oxygen or this one? It's the same. And then we saw that by asking which is a better structure. See, these are all fake. The true structure is really sort of a bond and a half between here. Okay, we got one bond and one bond. But there's additional bonding between here. But it's not full double bond because some of this electrons is in here. Ultimately, the true structure is something like this. So this is supposed to be 1.5 and 1.5. And this 1.5 is called a what? Bond order. That's a new term. Bond order is just, a single bond is 1, a double bond is 2, a triple bond is 3. This is a bond order of 1.5. And the electrons are through there. We get that, that's like pink. Usually I say red and white, and if it's a blend of red and white, we get pink. here we've got like 3 colors making a blend. Importantly, how do we know this? Well, evidence. If you look at this molecule, which CO bond will be longer, A or B? Why did you say B?
It's the same.
What's the bond order of B?
1.5.
I just drew it, 1.5. What's the bond order of A?
1.5.
The bond lengths are the same. Because really it's a bond and a half. You see, and we can tell that by X-ray crystallography. What we have here is resonance. Here's the important take-home point of why this works, because is the charge right on this oxygen? No, it's spread onto the other oxygen, as shown by this fake structure. And in the hybrid, we have partial minus here and partial minus here. The hybrid comes from blending those together. There's some minus on the oxygen. So does this oxygen have a full minus? No, it's only a partial minus, so it's more stable than the other one. The other one, the minus is sitting right there. It's not delocalized by resonance. Again, what we said at the very beginning could have got your answer. Does everybody agree that the extra lone pair is doing something? It's conjugated. It's more stable. There was a question over here first.
So there, I know you said that it's a blend of all those and it's shared, but since, I mean, there are electrons and there are atoms and there is going to, there are like discrete particles, so like versus time, there could be more over at one versus the other, so it's going to change. I guess I'm not really sure what is that what you just describe it as? It's as like an average then? An average?
Average of what?
That they are a 1.5
No, it's like
bond.
pink. Is pink an average of red and white?
But if you had a whole
No,
bunch of
pink
things.
is pink is pink. It doesn't fluctuate between red and white. It's just pink. But we have a limitation. It's hard to show. It's kind of cumbersome to work with, partial bonds. Pink is hard to work with. And so instead, we show red and white, which are easier to work with. But we say the true thing is really pink. It's really a blend. But then we can say, okay, pretend we're dealing with 2 resonance structures. Let's get rid of that one because that's so bad. Which one is going to, it's like these are parents. Is the kid going to look more like mom or dad? It's going to be equal because those are equal. The kid is going to look part like mom, part like dad. It's a perfect blend. Later on, we may not have perfect blends. Later on, the kid may look more like mom. She's a lot prettier. She's a lot more stable. Okay. All right, let's move on. Basically, that's an intro to resonance. Read about it. Guess what? We'll cover resonance during test 3. All right, but we just covered it all right there.
Just one quick question about the C atom. So can we say that the C atom is not truly trigonoplanar in this case? Because
Why is it not? I got a trigonoplanar right there. You see the trigonoplanar? That's a 120. It's 120 with a p orbital left over.
But even though the bond length for the 2 are the same, but the bond length from the C to C is going to be longer, right?
Why would it be longer? That's an sp2 hybrid orbital. Well, this is an sp3 over here.
Right.
Think about it. Okay, so that's resonance. In the end, what did we say? We gave the extra lone pair something to do because we put it in the p orbital. That guy over there, the extra lone pair, has nothing to do. It's sitting there in a hybrid. Okay, there's your answer. We can give it something to do called resonance. It's going to make it more stable. That's why decarboxylic acid is more stable than the alcohol, or more acidic than the alcohol. That's resonance. Down below. Sometimes resonance can outweigh inductive effects. Which one's more acidic? One on the left or right?
So right.
Well, there's your pKa's. Which one's more acidic? More acidic. Lower pKa, right? Okay. Why is that more acidic? Would you rather have minus on? By the way, are we talking about the NH or the CH? Or the NH. Would you rather have minus on N or O? But that's not more acidic. This one's more willing to become minus. Why is that one more willing to become minus?
The conjugation.
It's conjugation, because when it becomes minus, what's the hybridization of this anion? sp2, and one of the lone pairs is doing what? It's conjugated with not only one adjacent p orbital, it's got two adjacent p orbitals. Really doing something. This is a example where resonance actually makes this more acidic, even though that's oxygen. Resonance is very powerful. Fourth is hybridization effects. Hopefully you know your hybridization, or you're on your way to knowing it. See, how would hybridization affect something? We have two different orbitals. sp3 is longer. It means the electrons are further away from the nucleus if they're in sp3. If they're further away, they're not as attracted to the positive nucleus as much, so they're sitting out there and they're ready to react with the plus. The closer the electrons are to mom, the more they're kind of quenched and held tighter. Let's look at these hydrocarbons, just plain hydrocarbon. This is an SpCH. That's more acidic than the sp2CH, and that's more acidic than this. Why? Let's look at the conjugate base. If this gives up an H+, it forms this. By the way, I was just talking about being a base. We're actually talking about acids here. But it's the same argument, you just got to know which way you're going. If we consider the conjugate basis of these two, we get this and this. Which is more stable? Well, what's the hybridization of this carbon? It's still sp because it has two regions. This lone pair is in what type of orbital? sp. This lone pair, well, this is the one on the end. This lone pair is in what type of orbital? 4 regions, lone pair, and sp3. So which lone pair is held closer to the nucleus? The one in the sp. So which is more stable? The one out there or the one held closer to mama? The one held closer to mama is more stable. Okay? This is more stable because the LP is closer to the nucleus. Thus, which is more acidic? This one's more willing to give up the H because it forms a carbanion where the lone pair is closer to the nucleus. Alkyne CHs have enough acidity that we can do chemistry with them. These two guys, typically you don't do much chemistry, acid-base chemistry. But that's acidic enough that we will. That's a hybridization effect. Your hybridization effect is very important when you go to other atoms, though. It's the same argument we just used. Closer the lone pair is to mama, the more stable it is, the more it's okay. Let's go to bases. What do bases do? I've already heard it today, they accept an H+. I hate that word, accept. Because mechanistically, that is a bad word. They don't accept anything. They take. Okay? Accept sounds like it's sitting there and you throw an H at it, right? No. Mechanistically, you don't throw H at that. The bases go take them. Please say take. This base takes an H, and don't accept it. Accept it sounds like you're throwing it here and you get your arrows wrong. You lose points because you don't know how to use mechanism arrows. Bases take H's. Here we go. This is just like we showed at the very beginning. Lone pair takes H. These move on here. In this case, this is a base. That's the acid. How do we know that's the acid? it's got the H that's being taken. That's what the acid is, right? Okay. Of course, strong bases will have a high pKa for the conjugate acid. You should know all that. Bases do not have to be anions. What bases did you learn in Gen Chem? Your favorite base in Gen Chem is hydroxide. Okay, any other bases you learned? NH3. Okay, that's not an anion, that's neutral. Any other bases from Gen Chem? That's sodium hydroxide, that's lithium hydroxide, that's potassium hydroxide. That's magnesium hydroxide, that's hydroxide. This is ammonia. What is another base from Gen Chem? Well, water can act as a base. Anything can act as a base if it's got a long pair, but it's really not a base. Water is neutral. Okay? We got a lot more bases. In the end, what are your good bases? Bases are typically anions. Like that. But they can also be what? Many neutral nitrogens are also basic. Like that. Okay? Does water fit this description? Is it an anion? Is it a neutral nitrogen? So water is not a good base in my definition. All right? Anions or nitrogens? And with nitrogens, we'll actually say they have to be sp3 or sp2. Sp nitrogen is really not that basic because the electrons are closer to the nucleus. For each pair, predict strongest base. Which is a stronger base, ammonia or methylamine? What's the difference? Obviously, that's the difference. What do you know about the electronic effects of a CH3? Inductive effects. It donates. Okay? So which is going to be a stronger base? What does the base do? It takes an H. What part of the base takes the H? The lone pair. So do you want a lone pair that's like a big lone pair, with lots of electron density? Is that going to take the H? Or is it going to be a less electron dense lone pair? Let's put an H on just a Z. Okay, there's a dipole here, and there's a partial plus. We got a base. You want a little lone pair, or do you want a lot of electrons? Because see, that electron density can vary with electrons. Which one is going to be more eager to take this? A lot of minus here, or a little minus? Here I come. Boom, I'm taking the H, okay? With the bases, the more electrons, the more it's going to go grab that H. Which one has more electrons here? Okay? This donates, so what does that do to this region? It increases it. Okay? And this is like I gotta find an H. Now you can also go back to the acid and say, okay, both of these are minus regions. Now it's not a charge, but it is a minus region. And if we donate electrons towards a minus region, does that stabilize it or destabilize it? Things going to be neutral. If you got a minus region and you donate electrons towards it, it's going to make it more minus. Does that stabilize it? No. See, that's actually least stable, and you could make that argument too. The way I do it is right here. Donation makes this more minus is going to be more prone to go get the H. Let's see another example. Of course, when it reacts, what do you get? You should know you get that. Ammonium and hydroxide, right? Because here's our acid-base reaction. These electrons bond to the H. So we have a nitrogen with now not 3 bonds, but what does this arrow mean? Now it has 4 bonds, and that's, lo and behold, is a plus. These electrons move on to oxygen, becoming the third lone pair, and lo and behold, that's a minus. Your outcome comes from your basic mechanistic improvement. Okay? Question?
Probably not. Is NH3 only basic in water versus like a metal hydroxide could be basic in a polar solvent, or is it? No.
Ammonia is basic if you give it a strong enough acid. That's why you have to know pKa's. And judge equilibrium with your pKa. Do I know how to judge the equilibrium of an acid-base reaction? That's basically what you're asking, what you want to do. Next question. Number 2. Which one's more basic? Left or right? What's the difference here? What type of orbital is this lone pair in? Yeah, what type of orbital is this lone pair in? sp2. This is a true hybridization effect. Which lone pair is more out there reacting with H pluses? Yeah. See, this one is an orbital that's closer to mama. That one's more reactive. See, that other nitrogen is a little better parent. It holds its lone pair close to home. Doesn't let it get out there and react with protons. So that's a pure hybridization effect there. What do we got over here? Which one's more basic? What type of orbital is this in? What type of orbital is this in? The question is, what type of orbital is the lone pair in?
P.
That lone pair is in the p orbital, right? Busy conjugating with the p orbital next door?
The first one's a electron.
I'm sorry, that's sp3. sp3. Standard sp3 tetrahedral. So this lone pair is busy doing something. Is it going to get out there and react with H pluses? No, it's preoccupied. The lone pairs in p orbitals typically are not basic. There's a couple of examples where it kind of have some basicity. In general, a lone pair in the p orbital is busy doing resonance. Not basic.
Is that the whole basic reason why the p orbital or conjugated one is going to be less basic, because it's spread out more across the... I feel like we have...
Well, the less basic part is a consequence of it being spread out. It's busy doing something. It's not going. It has no interest in an H. Which one's more basic?
The right one?
Looks like this is extra, and this extra does what electronically?
Donated.
It's sp3 carbon chain. Donates. Which one is more basic? That one's more basic. Why? Why is that more basic?
Stronger lone pairs.
So maybe we're making electron density out more electrons.
Lauren? Why is that one more basic?
I don't know.
Want to take an educated guess about what we've been talking about?
Because that has.
It's got the extra alkyl group that's donating. What does the donation do to the anion? Does it diminish it or does it enhance it? Okay, if it's enhanced, is it going to be more eager to take an H or less eager? More eager. More electron density. Higher electron density due to the inductive donation of the alkyl chain.
So inductive donation is always going to go in the direction of the greater, I guess, electronegativity, is what you would expect. Like if that was a neutral thing, you wouldn't expect any inductive donation, correct?
Well, if it's neutral, it wouldn't be basic at all, and it wouldn't be a question. Which is more basic, ammonia or water? Probably all say ammonia, Jenkin. Why? Why is ammonia more basic?
It's less electronegative, so it's well,
I mean, they're both sp3 lone pairs. Oxygen's more electronegative. What does that mean? It holds them tighter. So is it? So is it gonna let it get out there and react with protons? No, it holds them tight. Oxygen's a good mama. Holds them close to home. Nitrogen lets them get out there and react with protons and get in trouble. Okay? But I've heard a couple of you say this already this week, that the oxygen was more basic. In fact, at the very beginning, when we looked at this drug molecule, didn't you, most of you say that you're going to put the H on the oxygen? I know some of you did. Let's go back and answer it now. Where's the most basic atom in this drug? Well, we got lone pairs there, 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 and there. Which lone pair is more eager and going to get out there and react with the H? Oxygen holds them tight, good mama. And nitrogen, not a good parent. Boom. What's the result? Well, do your reaction mechanism. These not those. These electrons do what? Make bond to H. What happens to the bonding pair? Moves on to chlorine as the bond breaks. Chlorine takes on 4 lone pairs. What do we get? I'm not going to redraw the whole molecule. We're having nitrogen with 2 methyls. What's now bonded to the nitrogen? Right here. An H. But that's no longer a typical nitrogen. Look for charge. What's the charge? That's actually a plus. And what do we get with it? Cl minus. We have an ion pair result. What do we call an ion pair? Starts with an S. Salt. A salt. Sodium chloride is the most common ion pair. That's the salt. That's the hydrochloride salt of Ultram from an acid-base reaction.
Professor, why in this case the chloride wouldn't go pull off a methyl group from the nitrogen?
Why would a chlorine not pull off a methyl group?
To
Why would it pull off a methyl group? What's your mechanism for that?
so I mean just because it's negative, right? Wouldn't it pulling off the methyl group stabilize both?
Yeah, but see, chlorine is a great parent. It loves being minus. It's an acid. And acids give up protons, and you're left with the Cl minus. That's the conjugate base. The conjugate base of a strong acid, is the conjugate base of a strong acid strong? No, the conjugate base of a strong acid is weak. This is weak because it's very stable. It's not going to do much. It will. We'll do some chemistry with it later on. This is acid-base chemistry. And by the way, what you're showing is theoretically, we could discuss it. Acid-base chemistry is always much faster and the first thing you want to consider. Okay?
So that same molecule, also, if you put it in hydroxide, then would the H on the oxygen should be...
If you put it in, if you react it with hydroxide, now you're asking this to be an acid. Well, that's clearly your base. Well, we want to do. You want to do that? What's the most acidic H? Well, this is easy.
One on the other.
Because there's only one H. All the other H's are on carbon. 3 H's on carbon. That's the acidic H. If you react with hydroxide, what would you get? That would take the H, and that would become what? O minus. And you'd make water, and then whatever was here would sit with the O minus. But that's not that acidic. So we have to know pKa's and say, okay, is that acidic enough that hydroxide will take it? So that takes us to where we want to move into next time. First off, what are your good bases? Anions and what? Nitrogens. Nitrogens, which is your more basic nitrogen? sp3 or sp? sp3. sp2 is also some basicity. When you get to sp, typically not basic. Okay? In nature, you see a lot of sp3 nitrogens and sp2 nitrogens in molecules, and they're called kind of nature's bases. They're neutral, but they're still basic. And in a lot of natural products, you see them, and they're called alkaloids. Alkaloids are alkaline, they're basic. Why? Because they typically have like an sp3 nitrogen, and that can act as a base. That's basic, that one's not. These are all examples of alkaloids. It's just miscellaneous, but it's sort of just a big, idea. Lots of alkaloids are like illicit drugs, or some are actually morphine. Morphine comes from the opium poppy. Okay. If you put acetyl groups on these OHs, you get what? Heroin. Okay. Please look at predicting equilibrium. Actually, we have a couple of minutes. That's the other hand. I can't see. Let's introduce equilibrium with the last 2 minutes we have. You react morphine with acetic anhydride. You put the acetyl groups on, you get heroin. Acetic anhydride is very coveted in certain regions of the world. It's sold on the black market. You take opium to heroin.
Is the acetyl group of CH2, CH3? Is the acetyl group of CH2, CH3, or is it more involved?
Acetyl from GenChem is that. Basically, instead of OH, you have O this on both OHs. That's heroin. It's less polar because there's no H there for hydrogen bonding, and so it gets into the brain easier. It's more of a psychedelic response. Okay, let's just see what we'll be looking at next time. Predicting acid-base equilibrium. Please read. And down here where there's blanks, try to fill in the blanks. I did one example here. These are basically acid-base reactions. Show what's formed. Probably also be asking you to predict which side is favored in the equilibrium. We'll also do a little bit with pH. This is Henderson-Hasselbalch. At a given pH, will acetic acid exist like this, or as the anion? Will it exist as the acid or the conjugate base? If a drug is in your small intestine where it's basic, how will it exist? Because if it's ionic, it may not get absorbed. So pharmacology, you need to know how things exist. There's some other miscellaneous things here. Show the acid-base reaction back here. And there's also a summary page where I'll sort of give you, summarize a lot of things, give you a few things to watch out for. That's at the very back with your acid-base chemistry. We'll finish that up next time, and we'll be moving into the other handout, alkanes. May have a quiz tomorrow, I'm not sure, but have a quiz. It'll be on everything we've covered up to now.